This video is about a method for computing probabilities approximately. It's a refinement of Monte Carlo approximation, so let's just review that first. In Monte Carlo approximation, we're given a random variable x and some function h, and we want to find the expected value of h of x. If we can't solve it exactly, we can approximate it computationally. First, draw a sample x1 up to xn from the distribution x, then just find the average value of h of x across your sample. Here's the typical way we use it. Suppose we want to find the probability of an event, say the probability that x lies in some set A. We'll use the standard link between probability and expectation. The probability that x is in A is equal to the expected value of the indicator that x is in A. This link between probability and expectation is totally trivial to prove, and it's so nifty for transferring tools about expectation of functions into tools for probabilities of events. But Monte Carlo isn't just for probabilities. It applies to any real valued function at all. Here's an example. I've picked a spiky h function, and I've chosen a uniform distribution for x, uniform over the axis you can see here. The true expected value of h of x is 3.21, which I got through an exhaustive integration of this function. When we use the Monte Carlo approximation, here I'm doing it with n equals 10 samples, we get an approximation. But it can be a very crummy approximation, especially with so few samples. Here I've marked out the sampled x points with a little notch under the axis. This is called a rug plot because it looks like tufts of a rug. And we can see that the sampling completely fails to pick up one of the spikes in h. If h has very sharp spikes, then we'd expect to need lots of samples to get a good approximation. Here's what it looks like with more samples. Even with 100 samples, we're still missing out the big spike. So what can we do to make sure that our samples hit the interesting regions of the sample space? The natural thing to try to do is to bias our sampling, so we get extra sample points in those regions. You can see that even with 10 samples, we're picking up the shape of the h function much better. Of course, we have to do something to correct for biased sampling. It's no good just talking to people who share your views and then saying everyone in the world shares my views. We have to correct for the fact that we're sampling from a biased distribution. Here's the way to do it. The method is called importance sampling. We pick any distribution, call it x tilde. We draw a sample x1 up to xn from x tilde, and then instead of the Monte Carlo formula, we use this formula here. This formula has a weighting term, this bit here, which gives a lower weight to regions where we're oversampling, i.e. where the likelihood of x tilde is bigger, and it gives higher weight to regions where we're undersampling. It's actually really easy to prove. I'll start by defining a function g that's the expression we're averaging. If I want to compute the expected value of g of x tilde, I can use Monte Carlo approximation. That gives me this sum over xi. Alternatively, I can write out the expected value as an integral. I integrate over all possible values of x tilde, and I multiply by the likelihood of the random variable at that point. Here I'm calling the dummy variable z, which is a bit confusing, but it's just a dummy variable, so it doesn't matter what I call it. This is nice because the likelihood terms cancel out, and I'm left with just the expected value of h of x. So I can write the ever so satisfying end of proof symbol, QED. All of this works for any sampling distribution x tilde at all. Whatever we pick, its likelihood function just cancels out. Well, sort of. I was actually a bit sloppy and I didn't take proper care about division by zero. There's a minor technicality. I should really have said this whole procedure works for any sampling distribution at all as long as it doesn't give divide by zero problems. It needs to have positive likelihood wherever h of x times the likelihood of x is positive. That's just a technicality, and it's easy to satisfy by choosing pretty much any sane sampling distribution. But the overall message that this procedure works for any sampling distribution x tilde, that's the message to take away. What's much more useful is to ask how good this approximation is. The whole point of introducing importance sampling is for situations where Monte Carlo takes lots and lots of samples, and we're hoping that by choosing a better sampling distribution, we'll get away with fewer samples. Our intuition said that we should bias our sampling towards regions where H is large. But, as I said, all of the maths on this page works for any sampling distribution at all, so that means we need to look somewhere else to find out what makes a good or a bad sampling distribution. So, how shall we measure whether or not this introduction of x tilde has improved matters? Here's a very simple idea. Let's just compute the variance of our importance sampling estimator. The approximation tells us to take samples of this thing here in brackets and average them, and if the variance is small, then the average should be well behaved and not noisy. Okay, so how can we compute the variance? Actually, we don't even need to compute the variance to figure out what the best possible sampling distribution is. Here's the perfect sampling distribution. We'll choose x tilde so that its likelihood is proportional to h of x times the likelihood for the random variable x at little x. The point of this is that it makes our estimator be a constant. In other words, it makes the variance equal to 0. Of course, this only works when h is non-negative. We can't define a sampling distribution with negative likelihood because that's just nonsense. Well, this looks perfect. But there's a catch, of course. There's always a catch. What should the constant be? Obviously, we need to choose the constant so that the likelihood for x tilde integrates to 1, because likelihoods always have to integrate to 1. But that's too hard. To make it integrate to 1, we need it to be 1 on the expected value of h of x, which is exactly the thing we wanted to approximate in the first place. Okay, so we can't get absolutely precisely the perfect sampling distribution just by this algebraic trick. But if we make some reasonable effort in this direction, if we try to bias in favour of h of x times likelihood of x, then we should get some benefit. And if we make a bad choice, we can end up with an estimator that's way worse than plain old Monte Carlo. Okay, so that's the general idea of importance sampling. There are two really important applications. The big one is autoencoder neural networks, which we'll look at in the next video. The other application is a simple way to do Bayes rule by computer. Let's finish off by looking through that. Here's the usual Bayes setup. We have two random variables, x and y. Bayes rule tells us a formula for the likelihood of x conditional on y. But this formula involves a constant kappa, and it's usually intractable to calculate kappa exactly using integration. So instead, let's ask the question, how can we compute an approximate answer for the posterior probability, the probability that x lies in some set A, conditional on an observed value of y? Here's an importance sampling calculation. First, we'll use our trick for converting probabilities into expectations. The probability that x lies in A is just the expected value of the indicator that x lies in A. Next, let me write this in a logically more consistent notation. Whenever we write out a conditional expectation, what we really mean is that we're taking the expectation over a conditional random variable. Here I've called the random variable x bar. Let x bar be the conditional distribution of x conditional on big Y equals little y. We want to calculate the expected value of h of x, where x has distribution x bar. If this seems like black magic, I suggest you just write it out explicitly as an integral, and you'll see that there's nothing funny going on here. There's no cleverness. It's just two different notations for exactly the same thing. Next, importance sampling. Importance sampling says that instead of taking the expectation over the distribution x bar that I really want, I'm allowed to take the expectation over any other sampling distribution as long as I stick in the proper correction factor. Here I've chosen the sampling distribution to be x itself. Now let's just do some simple algebra on the correction term. The likelihood of x bar comes directly from Bayes' rule, and this simplifies nicely. And this leaves me with an expectation over x, which I can do with the usual Monte Carlo approximation. I've also just renamed the likelihood term, I've called it Wi. There's still kappa to find, but we can approximate kappa by a deft application of what we've just proved, applied to the constant function h of x equals 1. I'll leave you to read through this. It's the sort of jujitsu maths that's better read than spoken. So, the whole point of this is that as long as we have the ability to sample from the prior distribution for x, and as long as we can compute the likelihood of y given x, we can estimate any probability we like for the posterior distribution. We don't need to do any maths to apply Bayes' rule, we can just compute the answer. So, that's computational Bayes' rule. The other application of importance sampling is neural networks for autoencoding, which I think is the most mathematically interesting topic in neural networks, and that's the topic of the next video.